In this tutorial we will create an environment in IsaacLab to train a robot to follow a black line using an image obtained from a camera attached to the robot. To do this, we will use Blender and create a stage on which our robots will run. In IsaacLab, we will see how to create camera, terrain, custom reward and termination functions. We will also create a custom convolutional neural network which we will use as a policy network in the Stable Baselines 3 library. Let's begin by installing Python 3 virtual environment. A virtual environment is a tool that helps to keep dependencies required by different projects separately by creating isolated Python virtual environments for them. Execute this command to create a virtual environment by the name IsaacEnv. After executing this command, a directory named IsaacEnv will be created in the home directory. Now we are going to install IsaacLab. Go to this page. Copy the link and clone the IsaacLab repository into your workspace. Install the CMake and build essential packages. These packages contain essential tools for building other packages from source. Now switch to the virtual environment we have just created. Move into the IsaacLab directory. Execute this command. If this message appears, install the IsaacRL package as suggested. After the installation completes, execute this command once again. Now we could install the IsaacLab successfully. To verify our installation, execute this command. If you encounter a CUDA error, it means that something is wrong with NVIDIA driver. To check what is going wrong, execute the NVIDIA System Management Interface command. This command is intended to aid in management and monitoring of NVIDIA GPU devices. It seems that we have to install a proper NVIDIA driver. Proper NVIDIA driver can be found by executing the Ubuntu drivers devices command. We will choose this driver because it is shown as recommended. After installing the driver, reboot your computer. Now, let's run the example once again. If you are launching IsaacSim for the first time, it may take some time before the application loads. We also have to download an IsaacSim GUI application. Go to this page. In this table, download the version suitable for your operation system. Extract the downloaded zip file. Open a new terminal and execute the post-install shell script. To launch application selector, execute the IsaacSim selector shell script. By pushing the start button, we can start IsaacSim GUI. Note that if you launch IsaacSim for the first time, it may take a while before GUI becomes operational. There are two zip files in the Google Drive. A program for IsaacLab version 1.4 and a program for IsaacLab version 2. Explanations will be done based on newer IsaacLab version 2.0 and IsaacSim version 4.5. But it seems that the new version still has several issues. So, if the training script for newer version does not work, please download the training script for older version and run it. Please download the line trace robot Isaac45 zip file from the Google Drive and extract it to your home directory. First, We will create a USD file of our robot. Move to the IsaacSim folder we previously downloaded. Open the IsaacSim application. Import the URDF file of the robot. In this tutorial we already have a URDF file of the robot, but if you only have a Zacro file of your robot, you need to convert it using the Zacro command. For details, please see this tutorial. We need to modify joint properties of the robot. Open the Joints folder. Modify damping and stiffness parameters. Because we will control rotation velocity of the wheels, to enable smooth rotation of the wheels we will set stiffness to 0 and damping to 1. For other 3 rotation joints which represent caster, we will delete the drive property because it should rotate freely. Now, save this USD file. The file that we saved contains information of the world and environment, whereas the USD file of the robot itself is located in the robot folder under the URDF directory in the robot description package. Now, we are going to create a stage on which line tracing robots will run. We will add texture to the STL file. STL file can be created using any CAD software. To add texture, we will use Blender. Download Blender from this page. Extract the downloaded tar.exe file. Run Blender. First, delete all objects in the scene. Import the STL file. Select the Modeling tab. Change Select Mode to Face Select. Select Material. Click plus, then New. Select a small circle on the right side of the base color label. Choose Image Texture. Select all faces of the stage. Then, press the U button on your keyboard. Select Smart UV Project. Press the Unwrap button. Now select the UV Editing tab. These are all unwrapped faces of the stage. Select UV menu. Click on Export UV Layout and save the PNG file. Minimize Blender for now. Now we are going to modify this PNG file. Move to Ubuntu Software. Enter Krita in the search text box. Install this software. Krita is a free and open-source raster graphics editor. Open our PNG file using Krita. Add whatever texture you need. Here, I will draw black lines on the white background. When you are done, save the image. Now open Blender once again. Open the PNG file we just modified. Select Viewport Shading. As we can see, we successfully added texture to our STL file. Now export the collada file and close the Blender. We also have a very simple URDF file to import stage with texture into the IsaacSim. We have just one link. Also, we have to specify STL file for collision calculation, and the collada file for visual geometry. Now open IsaacSim. Import the stage URDF file. Texture is successfully shown. Save this as a stage world file. The file that we actually will use for the simulation will be placed in the stage folder. Now let's see the code. In the MDP folder, custom reward function and termination functions are defined. Open the rewards Python script. Here, we obtain image data from camera in dictionary form. Here, we convert a colored image to grayscale. Because data is stored as dictionary, we have to specify key. In this line, we are thresholding our image. Here, all contours are found. Note that we have to invert white and black because this algorithm is applied to the white regions of the image. Here, center of each detected region is calculated. In this case, we assume that there will be only one region, that is the black line. Here, reward is calculated. Normalized distance is subtracted from 1. So, the further the distance between line center and the camera, the smaller the reward. Open the termination Python script. This part is the same as the rewards Python script. In this line, we calculate number of white pixels. Here we calculate the ratio of black pixels to the total number of pixels. If the ratio is smaller than a specified value, true value gets returned and termination happens. Now let's see the create line trace env Python script. The script is mostly similar to the one used in the previous IsaacLab tutorial, so here I will explain only the different part. Here, terrain is defined. As a terrain we are using the stage we previously created. In these lines, camera is defined. Note that we don't have to use any joints to attach the camera to the robot. Camera position and orientation is adjusted so that it looks down on the stage. The orientation should be specified using quaternion. This might be confusing for those who are not very much familiar with quaternions. So, here is a trick. Open the robot in IsaacSim. Attach the camera to the robot. Rotate the camera to the position you want. Change orientation representation to quaternion. You can use these values in the code without any calculations. Here, image size is specified. As observation terms for the policy, we specify image. the robot gets penalty for termination. That is, for losing the line from sight. And it gets bigger positive reward the closer it is to the center of the line. If the robot loses the line from its sight, the episode ends. Now let's see the line tracer folder. This folder is organized to register our files as GIM environment. In this tutorial, we register our environment as line tracer v0. For details, please see this tutorial. To create this folder, we followed the same procedure as described here. Open the sb3ppocnn.cfg YAML file. This time, instead of multi-layer perceptron policy, we use convolutional neural network for policy. N steps determines how many time steps are collected per environment before the PPO algorithm performs an update. Generally, batch size should be product of the n steps and number of environments. In these lines we define that our policy network will consist of a convolutional network part and a feed-forward network part. Open the train Python script. In previous IsaacLab tutorial we used this script as it is, but this time we add several modifications to it. Here, we import additional libraries to define a custom neural network. The convolution network part consists of 3 convolutional layers. Next, we flatten it to connect to feed-forward network. Here we define 2 layers of the feed-forward network. In the forward function, we use the permute because stable baselines 3 expects images in channel first format, but environment provides it in channel last format. Now move the train script into this directory. Also, move the line trace folder into this directory. Now we can execute training. When running the train script, specify task name, number of environments and enable camera. Unfortunately, with the newest IsaacLab version we have an error, which is probably a bug. But this should be resolved in the future. If we execute this using IsaacLab version 1.4 and IsaacSim version 4.2, the train script runs successfully.